Okay, so in today's lecture, we're going to move to what seems like a drastically different topic than what we've been covering, right? So up to now, we've looked at differentiation, we've looked at integration of real variable functions. Now, we're going to move to the third and final portion of Calculus 2, and that's sequences and series. And these topics might seem different, a lot different at first, but as the lectures go on, you'll see that everything is going to kind of come together, and at the end of the semester, you'll see how everything ties in, hopefully. Okay, so what is a sequence? Well, simply put, so the definition may be a sequence is a function whose domain is the positive reals. I mean, positive integers. Okay. And I think that a lot of students, when they first encounter sequences, are thrown off by the fact that like they don't realize that they're just really simple functions, right? So, as an example, you could have a function that looks like this. Where n is just some positive integer, right? This function maps the positive integers to whatever those numbers are, right? Now, this would be this is function notation. When dealing with sequences, it's common to use subscripts to indicate that the thing is indeed a sequence, which is a special case for function. So in place of writing this, the notation, so this is like the notation we'll use in this class, we're going to say that this will be a sequence maybe like A sub n, and that's equal to this argument. And for each positive integer n, you're going to have a term in the sequence. So what would this look like? So when n is, say, 0, then -1 to the power of 0 is just 1, so 3 plus 1 is 4. Well, actually, I'll just write it out. So like, and you can start n at 0 or 1. It just depends on how the sequence is defined. I'm going to start mine at 0. And then a sub n is this. So this will be 4. When n is 1, the sequence value is 2. Right, because you subtract off 1. When n is 2, you add 1. When n is 3, you subtract off 1. And what you're doing is you're building an ordered list that looks like this. Okay. Now, I should warn you that a lot of mathematics textbooks will adopt the notation to just know that this exists, that this is the same type of notation. And this notation is used in parentheses like this to indicate that there is an ordering on the list. But that's not how we're adopting, that's not the notation that your textbook and this course will adopt. We will use this, just know that that notation exists for the same sequence. Okay. Okay, so what would be like another example? Let's just say another example, maybe something like Bn equals to n over 1 minus 2n. Again, so this is just the argument of the function. So as we pass in values, as we pass in positive integers, we get out a sequence. So when n is 1, what do we have? 1 over minus 1. So when n is 2, we get 2 over minus 3, negative 2/3. Right? This would be 4, and then 1 minus 4 is minus 3 over 2. And then when n is 3, we'll have 3 over, what is that? Negative 5? Yeah. Negative 3/5. And then next one would be negative 4 over, 4 over negative 7, so forth and so on. Okay. Okay, so those are just examples of sequences. And what we will primarily be concerned with when dealing with sequences is convergence. Where are these sequences going? For example, as n goes to infinity, where is this sequence going? Is there a value that the terms are getting arbitrarily close to? And that leads me to the following definition, which I'm abbreviating for the sake of lecture. So we say that the limit as n goes to infinity of an is equal to some real number L is equivalent to saying that I hate trying to stay with your textbook's definition exactly, so I'm just going to say it how I know it. So for each epsilon greater than 0, there exists a positive integer m such that if n is greater than m, so such that n greater than m implies that the distance of the absolute value between a sub n and L is at most epsilon. Okay, so for each epsilon greater than 0, so epsilon, you should be used to it being in Cal 2, but this is just, epsilon is just some small real number, typically small, but it could be any real number. Right? So epsilon is typically some small real number, but again, this is for every real number greater than 0. There exists a positive integer m, and you can think of this as like m as like maybe like a cut off index. M is going to be an index, so that for all indices greater than this cutoff index, the distance from an to the L is at most epsilon. Now, it's my experience that students in Cal 1 never really grasp the ideas precisely behind the epsilon delta definition of a limit, which means that you'd probably not understand this definition and what it's trying to say. So I think it's best illustrated with a picture maybe. So suppose like these are, say, positive integers on this axis here. And then on this axis, this is like our function value, an. And so it looks like 1, 2, 3, 4, dot dot m minus 1 maybe, m plus 1 dot dot dot. I need to make my line a little bit bigger here. Again, this axis is positive integers, and it just goes on this way, right? And suppose maybe there is a number L right here. Okay. So suppose that you pick epsilon to be like, just, you pick epsilon, right? And we're going to suppose, so suppose first, like we're going to suppose that it's indeed the case that the limit of an is equal to L. And by the way, I find it annoying writing that all the time with sequences. With sequences, there's only one limiting value you can do. So in place of writing n going to infinity, I'm always going to write just lim. So limit of an equals L, just take it to mean that n is going to infinity. All right, so assuming that, we're going to see what this definition means, right? Because these are equivalents. That's what I wrote. So supposing that the limit is equal to L, there's L, I'm going to pick an epsilon. And suppose epsilon is like for example, like maybe pick epsilon to be a half. And so a half is like that, right? So then what I'm going to do is I'm going to make a little epsilon neighborhood around L. Okay? So that's like, that. So that right there is like L plus epsilon. That right there is like L minus epsilon. Okay? So maybe I shouldn't have wrote those n's there yet, actually. So what this definition says is that if that's the case, then what does it mean? So for each epsilon greater than 0, for any epsilon you pick greater than 0, there must exist a positive integer m. Okay? And what does that positive integer satisfy? It satisfies that if you pick any index greater than m, the distance in the sequence to the limit is at most epsilon. So anything that you plot past that m, so for example, suppose we get like, this is our m. Okay, so so if we start plotting our sequence, so maybe like A1 is like there, A2 is like maybe up here, A3 is like there, A4 is like there, A5 is like there, AM is like here. This is all fine and dandy, right? This is okay. But since this definition is true, and that's the m that we got for that epsilon, everything past this point better be plotted in there. So they can be there, there, there. Everything must be inside of here. Off to infinity. Everything. Right? And this, for every positive integer greater than n plus 1, the distance is measured by taking the absolute value of the difference. So you can think of this as just the distance from AN to L. So this is distance from AN to L. if I look over here to the y-axis, each of these points is in there, which means that they're all falling somewhere in here. All of the sequence values after m are inside of here. Yes, there are sequence values that are outside of it. Right? There are those values, but everything after m, the y values are going to be inside of there. So why would this definition make sense for a limiting value? Like, where is the sequence going? Well, if we pick, well, before I get to that, I wanted to point out something, that m is just some positive integer, which means that 1, 2, 3, 4, 5, up to m, all those sequence values are like, there's a finite number of them, right? 1 through m. But then after m, this goes on to infinity, and all of those values are inside of this interval here. So what that means, like kind of not intuitively, but the idea is, I guess, that there's a finite number of terms outside of this interval from the sequence, and an infinite number of terms inside of there. Okay? An infinite number of terms in the sequence have to lie in there, because if we're assuming that after that m, everything falls in there, and there's an infinite number of points, so like all of the sequence basically is crowding around L, and there's a finite number of points that don't. Well, since we're assuming that this holds, we could pick an arbitrarily small epsilon. This has to hold for any epsilon greater than 0. So we could pick, like, I don't know, like epsilon equal to like 0.0000000001. And then there'd be a smaller interval, possibly around L, like a tiny little interval. And at some point, if we're assuming that this holds, at some point, there needs to be like an M prime, maybe, a green M, where all of the points after that lie in there, which means that there's an infinite number of points squeezed up next to L inside this tiny interval, and only a finite number up to here that aren't. They're clustering around L. As you go off to infinity, no matter how small of an interval you pick, if this is what's true, it better satisfy this definition. So no matter how small of an interval you pick around L, eventually, far enough down the line with your indices, they all become very close to L. That's all that the definition is saying. Okay. So the sequence definition relates nicely with definitions for functions of real variables. So I should just probably note that I think that your book even makes it a theorem, so I guess I'll write that out. Okay, so f is a function of real variables. I'll just say a function of real variables. With the limit as x goes to infinity of f of x equal to L. And AN is a sequence with f evaluated at n equal to a sub n for all positive integers. n, then the limit of a sub n is equal to L. Which is, it makes sense, right? Like, so I guess like maybe an example for like, we know that the limit of 1 over x as x goes to infinity, we know that equals 0, right, for real numbers. So it would make sense then that the limit of 1 over n also equals 0 for natural numbers. Okay. And again, remember, I'm not going to write the subscript when I'm taking the limit of sequences. I just find it redundant. Because with inputs for sequences, you can only really consider, the only interesting things are to take in going to infinity. That's the only real limit there is, so there's no need for writing in going to infinity. Unlike with functions, where you can have interesting things happen when x goes to -2 or something. Like that's a thing, or x goes to pi. Like that's more interesting, but with sequences, there's no need. Okay, so based off of this theorem, you should expect the behavior of limits of sequences to satisfy all the standard properties of limits of functions. So properties. So maybe say, suppose the limit of a sub n is equal to L, and the limit of b sub n is equal to k. Okay, just suppose that. Well then, maybe part 1, the limit of c times a sub n is equal to c times L for any constant c. 2, the limit of a sub n through addition or through subtraction with b sub n is equal to L plus or minus respectively m. Oh no, so not mk, sorry. Part 3, same thing for products. The limit of the product is the product of the limits. And part 4, again, the ratios. So the limit of the ratio of a sub n and b sub n is equal to the ratio of the limits, provided b sub n is never equal to 0 and k is non-zero. So all the standard limit properties that you have in functions hold for sequences, because sequences are functions. Okay? This is a very specific type of function, a function with a specific domain. Okay. Yeah. So what do I have next? Okay. Oh, looking at convergence of a sequence. So maybe let's look at does the sequence converge? Actually, I don't even need to write this thing. I'll just say it out loud. For the following sequences, determine if the sequence converges, and if it does, find the limit. So sequence a sub n equals to 3 plus minus 1 to the power n. Oh, that's the sequence that we started with at the beginning of class. So we already know what this looks like. It looks like we say 2, 4, 2, 2, 4, right? Add 1, subtract 1, add 1, subtract. So when it's even, it's going to be 4. When n is odd, it's going to be 2. This alternates between 2 and 4 forever, so that's not going to converge to anything. Right? What about b sub n equal to maybe n over 1 minus 2n? Okay. So now, if we look at the terms of this sequence, we see that it's going to be, so, oh, this is the one we looked at the very beginning. So it's minus 1, minus 2, so there's going to be 4, so minus 2/3, minus 2/5, minus 2/7, but no, not 2/5, 3/7, right, 3/5, and then 4/7. Okay. Now, maybe it converges, maybe it doesn't. One way to deal with this type of sequence, though, is a technique that you probably learned when taking Cal 1. And that is to look at the thing and look at the ratio and then just divide out all the n's by multiplying by a special form of 1. The special form of 1 that I'm going to choose to do is 1 over n all over 1 over n. That doesn't change the values, it's just 1. So what is this going to become? So n times 1 over n is just 1. 1 over n, I mean, 1 times 1 over n is just 1 over n. Minus 2n over n, so just minus 2. Right? That times that. And we know that the limit of 1 over n goes to 0 because we know that 1 over x goes to 0 for real values. And this becomes negative 1/2. So it does converge. Okay. Let's look at another example. So we have C of n equals to, what is it, n squared over 2 to the power n minus 1. Okay, so right away, before we even start writing up the terms of the sequence, what do you think? Do you think that this is going to converge or not? Well, what do we know about the numerator? It is a polynomial of n, right? In the denominator, we have an exponential. Which grows faster as n increases? The polynomial or the exponential? The exponential is definitely going to grow much faster than that n squared business. Right? Like just put in 100 into n. What do you get? Like 100 times 100? How does that compare to 2 to the power of 100? There's a huge difference. So right away, my intuition is telling me that if n is huge, like a billion, the numerator means basically nothing and the denominator is taking over. Which means, in my opinion, it's going to converge to 0. But how can we show that formally? Well, whenever I see things involving ratios with exponentials and limiting processes, I think of Lehobital's rule. So I'm going to say maybe let f of x be this function of be this real variable function, and then I can take the limit as x goes to infinity of f of x, and I get infinity over infinity. I already saw that coming, but whenever you get this indeterminate form, you can just apply Hopital's rule and take the derivative of the numerator and the derivative of the denominator. So that'll be 2x over, what is that, natural log of 2 times 2 to the power x, right? So just you have to remember that dx of 2 to the power x is equal to natural log of 2 times 2 to the power x. And then I see 2 over 2 to the power x, which is going to be equal to the limit as x goes to infinity of, I can get rid of the 2's and just write this. So that'd be 2 to the power x minus 1 maybe. Now, if I evaluate this, I still get infinity over infinity, which means that I have to apply Hopital's rule again. So, okay, keep on going. Derivative of the numerator now is just 1. Okay, finally, we get rid of the x variable. And then the derivative of this is, so hopefully all of you remember that it's just going to be, that's like your u, it's still going to be equal to natural log 2 times 2 to the x minus 1 times the derivative of the exponent, which is just 1. So it's just going to be this. So that natural log of 2 is going to be hit again, and it's going to become squared. And then we're going to still have 2x minus 1. Now, as my intuition at the beginning held, this is just going to go to 0. Okay. Now, since this goes to 0, and the sequence is equal to the function for every positive integer, we conclude that the limit of Cn is equal to 0. Done. Okay. So the standard limiting techniques that you know from real variable functions will also be valid for sequences. It's kind of it's an easy thing to transition to if you knew all the rules for these limits for the previous functions well. For example, if any of you remember the Squeeze Theorem from Calculus 1, there's an analogous Squeeze Theorem for sequences, obviously because sequences are still functions. So just write it out formally, Squeeze Theorem for sequences. It's a little bit different, but it's still the same concept. Okay, so if limit of an is equal to L, which is equal to the limit of Bn. Okay, so suppose you have two sequences that we both converge to the same limit L. And there exists a positive integer n so that an less than or equal to cn less than or equal to bn are all little n greater than capital N. So basically what it's saying is that, so you have two sequences an and bn, they converge to the same number L, and then also the sequence cn, after a certain point, after an index, call it n, that sequence is always in between an and bn. Then the sequence in the middle has been squeezed, and it will have the same limit as the other sequences. So then limit of cn is equal to L. Okay. Now, again, it's slightly different than what you know for real variable functions, but it's actually almost, to me, easier. It's just, at some point, Cn must be between these two things, and at some point, these things go to L. This has to go to L as well. Okay, so this has a nice application to build another theorem. Okay, so if an is a sequence with the limit of the absolute value of an equal to 0, then the limit of an is equal to 0. And this is just a straightforward application of, why did I write 0? I'm pretty sure that holds for sequences without 0. Like it converts to other numbers. Just to be cautious, I'll leave it at 0. Okay, so why is this true? Let's just find the squeeze theorem. If you want to prove it, just say something like, let an be a sequence with limits the absolute value of a sub n equals 0. Then maybe further observe that by definition, minus of the absolute value of a sub n is less than or equal to a sub n, which is less than or equal to the absolute value of a sub n. By definition, right? Right? So, since the absolute value converges to 0, the squeeze theorem is going to say that a sub n converges to 0. because this is going to 0 and that's going to 0. So maybe just say that, like maybe since negative a sub n converges to 0, and positive absolute value a sub n goes to 0 as n goes to infinity, maybe. We conclude that the limit of a sub n is equal to 0. If I had room, by the squeeze theorem. So that's what I would write next, and then you'd be done. And then you put a little QED square. Okay. So, how can we use this? Well, let's consider the sequence C sub n equal to surely I wrote this down wrong. This example seems trivial. I need a better example than this. Why is it so dumb? Let me see. Give me 1 second. Yeah, I guess this is the one I had in mind. Kind of a silly example, but all right. So here, this is in factorial. If you haven't seen that before, this is in factorial. I should probably define that for you, just in case you haven't seen it. So in factorial is equal to the piecewise function. So 1 if n is equal to 0, and then otherwise 1 times 2 times dot 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 times n minus 1 times n. Otherwise. Okay, so just to illustrate, like 4 factorial is equal to 1 times 2 times 3 times 4, which is 24. And 5 factorial is equal to 1 times 2 times 3 times 4 times 5. But notice something when dealing with factorials, especially computer science majors in here. You can group together and factor factorials nicely. So, for example, notice right there, that's 4 factorial. This is like 4 factorial times 5, right? In fact, n factorial is really n times n minus 1 factorial. So what is this number? Well, it's just that times 5. So 120, right? Okay. So just be aware of that. I know that's not involving, I'm kind of on a tangent right now, but let me just show you something because I think there's problems in the textbook about it. Like if you were to look at 4 factorial over 5 factorial, that's just 1 over 5. Because 5 factorial can be written as 4 factorial times 5, divide out all those numbers, and you're left with just 1 over 5. Just keep that in mind. Okay, so so how can we look at this thing here? Well, we need to, obviously, by the way, obviously it's going to 0. Hopefully you see that because the thing on the numerator is just oscillating between 1 and negative 1, and that denominator is just going to 0. It is going to 0. So if we can somehow use another function that we know about to squeeze it to 0, that would be nice. So maybe, I do know that exponentials grow faster than factorials. I know that through this experience, but maybe we can use like 2 to the power n or something, right? Like, let's compare this to, like, I'll maybe say like an equals to negative 1 over 2 to the power n. And then maybe like bn is equal to positive 2 to the power n or something like that. Okay. So what if this denominator is always bigger than that denominator after a certain point, then this is always going to be smaller than that, right? But no, sorry, the exponentials, well, we're about to find out which one grows faster. I just forgot. So let's just take a look at what they are. So n factorial is equal to 1 times 2 times 3 times 4 times 5. I'm going to write out a few so I can get a sense of where we're at. Times dot 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 times n minus 1 times n. Okay. Now for the same value of n, we just have a bunch of 2's, right? 2 times 2 times 2 times 2 times 2 times 2 times dot 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 times 2 times 2. Okay, so let's just compare them and see which ones are bigger. So, all right, so when n is equal to 1, 2 is greater than 1. Okay, so that's bigger than that when n is equal to 1. When n is equal to 2, we have 2 versus 4. That's still bigger, okay? When n is equal to 3, we have 6 versus 8. This is still bigger. When n is equal to 4, we have 24 versus 16. So starting here, that became 24, that became 16. And that's a pretty big jump. And then 24 times 5, that's 120. This is next going to be 16 times 2 or 32. 120 versus 32. That's, now we start to see that everything past n is equal to 4, the factorial is going to be much larger. So, for n greater than or equal to 4, 2 to the power n is strictly less than n factorial. Which means if I chose these two sequences here in comparison with this sequence, I see that, so negative 1 over 2n is less than or equal to negative 1 to the power n over n factorial, which is less than or equal to 1 over 2n. So we have an, bn on either side of this function. And we know that this goes to 0, that goes to 0, which means that that goes to 0. By the squeeze theorem. Because after n is equal to 4, it goes away. Yeah, so since limit of negative 1 over 2n equals 0 equals the limit of 1 over 2n limit of Cn equals 0 by the squeeze theorem. I was almost going to say we could probably use this guy, this absolute value, but this squeeze theorem is all we need. Okay. So also, you're going to be asked to find patterns. Like given a sequence, I want you to find the explicit formula for the nth term of that sequence. So suppose, for example, like I give you this sequence, like 2, 4 over 3, 8 over 5, 16 over 7, 32 over 9, ... So what is the explicit form of this sequence here? Right away, what do you notice? They say there should be something quickly noticeable here. I immediately notice that if I put this over 1, then I see that 2, 2 squared, 2 cubed, 2 fourths, 2 fifths. So if I'm going to make a sequence, I'm definitely going to have a ratio where the numerator is 2 to the power, so 2 to the power 1, 2 to the power 2, 2 to the power 3. So it's like n is equal 1, 2, so it's like that. Now, what about the denominator? I immediately notice something about the denominators as well. The denominators are odd positive integers. So it's like there's 2 ways to express an odd integer. You can have 2 times n plus 1, but that's like equivalent to 2n minus 1. It's just twice an integer minus 1. So how does this look? So when n is equal to 1, this is 1. So 2 times 1 minus 1. When n is equal to 2, 2 times 2 minus 1. Yeah, that looks like it's it. Here, I think that's the sequence. Okay. Now, does the sequence converge? My immediate guess, what do you think I guessed that this converges to? I could be wrong, but I have a guess. Think about it. My guess is that it converges to 1. Why do I think it converges to 1? Well, oh no, wait a minute. Sorry about that. My immediate guess is that it diverges, not converges. If that would have been 2 to the power n, I would have thought it converged to 1. I was just looking at it wrong. Because it's 2 times n, right? This numerator is going to grow much faster than that denominator. Right? So because the numerator is going to outpace the growth of the denominator, which we can measure by taking the derivative of the top and the bottom, basically Lehobital's rule, I bet you it's going to diverge. It's not going to converge. So if we look at the limit as x goes to infinity of 2 to the power x over 2 times x minus 1, I already know that that's infinity over infinity. We can apply Lehobital's rule. And these are for real, this is like a real variable now. Again, if it converges for the real variable, then it will converge for the sequence version. So what do we have on top? We have natural log of 2 times 2x. And then in the denominator, we have just a 2. And yes, that goes to infinity. So a sub n diverges. And that's the terminology we use when the sequence doesn't converge. Okay. Okay. So one more definition and then a theorem, and I think that'll be it for today. So 2 more definitions, and they're long ones too. So definition. So a sequence a sub n is monotonic if it is either non-increasing that's like a1 greater than or equal to a2 greater than or equal to dot 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 greater than or equal to an greater than or equal to forever. So it's non-increasing or non-decreasing. Did I read that? Yeah. Why did I just have a brain point? And this is just the opposite inequalities. 1 less than or equal to a2, which is at most a3, dot dot dot, which is at most an, and this just keeps on going forever. So these are monotonic sequences. Okay. Now that we have monotonic, there's one more definition a sequence can satisfy that is of interest to us, and that is the notion of being bounded. Bounded from above, bounded from below, but in general just bounded, and that's what I'm going to write down. Okay, so definition, a sequence an is bounded if one of the following holds, one or more of the following holds. I know. If both hold, that's this I'll say. Both of the following hold. If both of the following hold, I'm trying to shorten the definition that's in your book. It's really long. No, just I have to do it this way. So for some integer m, a sub n is at most m for all little m, or little n. So this is what it means to be bounded from above. And for 2, for some, I guess, integer m again. A sub n is greater than or equal to m for all n. It just means that the sequence can be no more or no less than a given number. I like to think of this more generally. This is how you would learn it in like a real analysis class, just that the absolute value is at most m for some integer m. That takes care of both of these. Your textbook uses 2 different definitions. It's fine, but just more writing for me to do on my small board. Okay, so hopefully we understand what it means to be bounded. And we can prove a theorem. I feel like I don't prove enough theorems in this course. Do we really need to prove a theorem? About being monotonic and bounded together, what does that mean about the sequence? Yeah, we'll prove it. Okay, so theorem. A bounded and monotonic sequence converges. Bounded and monotone sequences converge. So a lot of times when you're looking at sequences, you really won't be able to find the limit, or you don't even care to find the limit. You just want to know if the limit exists. Does the sequence converge? So, for example, if your sequence is somehow telling you the error in an algorithm, or like the number of procedures in an algorithm that as the number of input, like the size of the input increases, and you want this number to go to 0, the error for each iteration, or the number of iterations per input size, these things can measure performance. And you want this sequence to go to 0. Or you want it to converge to some number. You don't want it to vary around too much, right? So just the idea that this thing will converge will tell you something about the performance of the algorithm you're looking at, or something like this. Right? So if you know that your sequence is bounded and monotonic, then we know that it converges. That's what this theorem says. We might as well prove it, but it should make sense. Like, for example, if you're bounded from above and you're monotonic increasing, what's going to happen? Eventually, you're going to have to run into a wall somewhere, and that wall will be your limit. Okay, so in order to prove this, I do have to state something about the real numbers. It's called the Completeness Axiom. And it says that every bounded set of real numbers has it says that a set of real numbers bounded from above has a smallest upper bound. That's what it says. So a set of numbers, of real numbers. So a set of reals bounded from above smallest upper bound. That is the completeness axiom, and we'll make use of that when proving this theorem. I know most of you are math majors, you don't care, but even computer science majors, you need to know how to prove things, you need to observe proofs. So what we're going to do is we're going to do this in the case that the sequence is bounded from above and is monotone increasing. The same thing works for bounded from below and monotone decreasing. So we're going to say let A sub n be a monotone increasing or monotonic increasing monotonic increasing, or I should say with the terminology here. If I want it to be increasing, I'll say non-decreasing. So let A sub n be a monotonic, non-decreasing sequence which is bounded from above. Or bounded above by, I don't know, M or something. Was I using M earlier in the definition of the sequence, the convergence of sequences? Dang it, it was. Let's just K, whatever. Use K, because I was using M in the definition of convergence earlier. I don't want to confuse you. So just make this something as your K. That way it's not confusing you. And so we're going to suppose that this sequence is bounded above by K. Okay? Okay. By the completeness axiom. So if this sequence is bounded above, then it's a collection of real numbers that is bounded above. It has a smallest upper bound by the completeness axiom. So by the completeness axiom, this collection of real numbers, this sequence has a least or smallest upper bound. Call it L. Mathematicians like to go maybe say L. So that's what we're calling the smallest upper bound. So if you look at the terms of your sequence, like suppose this is like your y-axis, right? As you're going off to infinity, and here's L, it is your smallest upper bound, and you have all these terms that are bounded above by L, right? And it is the smallest one, right? So if I subtract off anything from L, call it epsilon maybe, anything, then if that's the smallest upper bound, then there is another point in the sequence that passes by it. Otherwise, L wasn't the smallest upper bound. So if epsilon is greater than 0, then L minus epsilon is no longer an upper bound for A sub n. A sub n. Okay, so at some point there's going to be a term that goes in there from the sequence. Call that term maybe little a sub capital M or something like this. Okay. And then, oh no, we can say, I think your textbook likes to use capital N. Yeah, capital N maybe. Well, yeah. So, but notice how I was going back and forth earlier? We have to remember that the sequence is monotonic. So since it's monotonic, it's like this. So it's like there. It's always increasing. It's monotone increasing. So what do we have? L minus epsilon is no longer an upper bound. So there are, I'm just writing out the definition of not being upper bound first. So there are terms from the sequence with L minus epsilon strictly less than a sub n. Okay. For some values n. In particular, for all little n greater than capital N. For all n, little n greater than capital N, where, running out of room, where a sub capital N is the last term less than L minus epsilon. Right, so it's increasing because it's possible that we picked too big of an epsilon, and I think your book even didn't take this nicking, where a sub n is the first term with a sub capital N greater than L minus epsilon. Right, so there has to be at least one, and there's one in there. I don't like the way this reads. So there are terms with, yeah, I'm going to fix this for you. I hate writing proofs like this when they just don't read right. So let's take a moment, come back up to here. Let this a sub n be a monotone, non-decreasing sequence, which is bounded above by k. By the completeness axiom, this collection of numbers, real numbers, has a smallest upper bound, call it L. Now, I'm going to fix what I have here and make it read much nicer. So I'm just really picky about this since I am a mathematician. So we call it L. So this is the least upper bound. Then, since it's the least upper bound, we have then, by definition, L minus epsilon is no longer is, to save room, is not an upper bound. Is not an upper bound for the sequence A sub n. Okay? That's just because this is the smallest one, so if I subtract anything off of it, it can no longer be an upper bound, right? Because that is the smallest upper bound. So since L minus epsilon is not an upper bound, and since L minus epsilon is not an upper bound, there exists a positive integer following capital N, so that that term from the sequence with that index is greater than L minus epsilon. Okay. All right. So, but then, however, or no, maybe further, or maybe not since. No, since is there. Moreover, A sub n monotonic non-decreasing implies that, together with this inequality here, L minus epsilon less than A sub n less than or equal to A sub little n, but that's at most L, which is strictly less than L plus epsilon, for all little n greater than capital N, because it's monotonic. Right? Because this is going to be greater than that if the index is bigger, but none of these terms are bigger than the smallest upper bound, which is strictly less than L plus epsilon. So what have we shown? Hence, if this is, so what is it saying? L minus epsilon is less than A sub n, L plus epsilon is greater than A sub n. It means that if we just add L, or I mean subtract L from both sides, we get that minus epsilon less than, this is probably like, I should probably just say it. L minus epsilon, L plus epsilon, A sub n is at most that, at least that, for all n greater than or equal to n. Hence, the limit of A sub n converges to L. Because it's in the interval between L minus epsilon and L plus epsilon, so that is in the interval with L. For any choice of epsilon, which means it converges. And for any choice of epsilon, we get that there is some first term that's greater than this, which implies this, which implies that the sequence is always within epsilon distance to L. I was going to write out, I didn't, but we can just go ahead and finish the proof there. I was going to write it out that this implies that minus epsilon is at most a sub n minus L, which is at most positive epsilon. This, if something is greater than minus this and less than the positive of that, that implies that a sub n minus L is at most epsilon, an absolute value. So that's what I didn't write out in the proof. Okay, I think that there's enough proof for you to get the general idea. So how does this work? Let's look at an example maybe of using that theorem. Maybe B sub n equals to 2n over 1 plus n. Okay. So if it's bounded and monotonic, then it's convergent. Okay. I know that it's convergent. What do you think it's convergent to? I bet you it's 2, but we don't. I just want to know if it converges. So is it bounded? So I claim that this sequence is bounded above by 2. Okay. So suppose that it's not. So this is what I claim. Suppose not. And n is a positive integer. So maybe I'll prove this too. Suppose not. That is 2n over 1 plus n is greater than 2 for some values of n. Oh yeah, I should probably say that this, I claim this holds for all positive integers n. Right? So suppose not. That is that it's greater than for some integer n. But then if we suppose that if we multiply both sides by 1 plus n, which is a positive number, it doesn't change anything, we get that 2n is greater than 2 times n plus 1. A contradiction. That can't happen. Why can't that happen? Because that's greater than that. So the inequality is in the wrong direction. So this thing is bounded above. Is it monotone? Let's just check with some values of n. So when n is equal to 1, we have 2 over 2, which is just 1. When n is equal to 2, we have 4 thirds. When n is equal to 3, we have 6 fourths. Okay. 6 fourths is just that's 3 halves. When n is equal to 4, we have 8 fifths. And it definitely looks like it's going to be monotone. How can we check that? Let's just see what happens. So this is like the previous term. And then the next term would be this. We don't know the direction yet, so I'm just gonna put like maybe let's go by contradiction. Let's just suppose that for some n it's greater than. like it's not monotone. Then if we multiply both sides by that and by that, we get 2n times 1 plus n plus 1 greater than 2n plus 1 squared. Again, this is, we're assuming the wrong direction. We're going to show that it's a problem, right? So then we get 2n plus 2n squared. I know, that's 1 plus 1. So that'd be 2, so this would be a 4n plus 2n squared. And we still don't know about that inequality. And then this would be 2n squared plus 4n plus 2. Yes, that can never be the case. Right, this is like a sub n, and this is a sub n plus 1. So that can never be greater than that. So it is monotone increasing. So by that theorem, which I call the monotone convergence theorem, this does converge. Okay. And then there's all sorts of examples in the textbook that you're going to have to read. You will most definitely need to read this section, section 9.1. As far as suggested homework problems, 9.1 homework, all I have is 5 through 48. Okay. All right, this week is going to move fast, so please keep up with the videos, and I will post another video tomorrow. And more than likely, you'll start seeing exam grades on Blackboard pop up tonight, hopefully. That'll be it for this video.